Here we have a nice algebra problem, and we are given an logarithmic equation, and we have to find the number of real roots for which x is greater than 1. Let's start with this equation, which is log 2 by x at base 2x multiplied by log x at base 2 whole square plus log x at base 2 whole power 4 equals 1. So now we can let that log x at base 2 is equals t, some variable. So we can simply rewrite it as log 2 by x upon log 2x, since we know if log n is at base m, so we can simply rewrite it as log n upon log m. So I use this property of log over here, and now further we can replace this by t square plus t raised to the power 4 equals 1. And now we can rewrite it as log 2 minus log x divided by log 2 plus log x multiplied by t plus t raised to the power 4 equals 1. Now we can take log 2 common from the denominator and the numerator, so we'll get 1 minus log x divided by log 2, 1 minus log x divided by log 2 of t plus t square plus t raised to the power 4 equals 1. And here this expression can be written as 1 minus log x at base 2 divided by 1 plus log x at base 2 multiplied by t square plus t raised to the power 4 equals 1. And now we can simply replace it by t, what we assumed here. So we can rewrite it as 1 minus t upon 1 plus t multiplied by t square plus t raised to the power 4 equals 1. And we have to solve this equation. 1 minus t upon 1 plus t multiplied by t square 1 minus t raised to the power 4. And now we can factorize it, and we'll get 1 plus t square 1 minus t square, and in left hand side 1 minus t divided by 1 plus t multiplied by t square. And if you see, then it can be more factorized, so we can write it as 1 plus t multiplied by 1 minus t, 1 minus t upon 1 plus t multiplied by t square. So here comes the two cases. When we are just cancelling it, then it implies that 1 minus t is not equal to 0. It's a non-zero term. So this is our case 1. And the second case is when we are letting it equal to 0. So I'm going to consider my first case when these terms are non-zero. So I'm just cancelling it, and we'll obtain t square upon 1 plus t equals 1 plus t square multiplied by 1 plus t. So we'll get simply t square equals to 1 plus t square 1 plus t whole square. So we can simply expand this, and we'll get t square equals to 1 plus t square multiplied by 1 plus t square plus 2t. And after multiplying these two factors, we'll obtain 1 plus t square plus 2t plus t square plus t raised to the power 4 plus 2t cube, and t squared in the left hand side. We can simply cancel out these two terms and we'll simply obtain t raised to the power 4 plus 2t cube plus t square plus 2t plus 1 equals 0. So since in the coefficients of this fourth degree equation there is no change in the sign, so we can simply say that there is no positive roots. By using the Descartes sign rule, we can simply conclude this, and our t is log x at base 2. So if the value of t is smaller than 0, then it implies that x is smaller than 1. So by this first condition we not found any roots which has the value x greater than 1. So we have to now consider our second case where 1 minus t is equals to 0. So here we can start with our second case, which is 1 minus t is equals to 0. So we can substitute the value, which is log of x at base 2 equals 0, and we can get log of x at base 2 equals to 1, which simply implies that x is equals to 2. So here is the only one possible roots, which is t equals to 1, where x is equals to 2, which means x is greater than 1. So the number of roots for value x greater than 1 is 1. So we have only one root for which x is greater than 1.